All right, so today let's talk about vectors, scalars, distance, and displacement. Again, these notes are already set up in Cornell Notes format. I encourage you all to write these down exactly as I have them because I do think that these are a very good format to start off with. Only thing I do ask you to add in addition to what I have written down is the date of your notes and a summary, 1 to 2 sentence summary about what you learned at the end. All right, so let's zoom in on our objective for today. So the objective is to determine and describe the difference between vectors and scalars by evaluating the position, distance, and displacement of objects. And our topic again is on vectors and scalars and distance and displacement. The essential question you all should be answering by the end of watching this video on notes is what is the difference between a vector and a scalar, and what is the difference between a distance and displacement. So you all should try to summarize that in the summary at the end of your notes today. All right, let's move on to chapter 1 of our notes. The first question we're going to be answering is, how do we determine the position of an object? Well, let's first define what position really means, especially in terms of physics. So position is defined as simply where the object is located. Where is it located in space? So this is one of our vocabulary terms for today. So position, where an object is located. We use the variable x to represent position. So think x, I always like to think x marks the spot, right? When you look at a map, you are trying to find the treasure, right? And so your starting point here, and I'm going to do that in a different color. So we've got our starting point, right? And then we are following the trail to the treasure. Okay, so a position on an coordinate diagram, right? We could just mark this, and I'm still in highlighter mode. We could just mark this with an X, wherever that person is, okay? So wherever the object is in space, okay, if the object has traveled, we're gonna mark where it is with an X. So our variable for position is X. And again, the position is simply where an object or a person is located in space. Okay, so now let's talk about what a scalar and a vector is. So these terms you might not be as familiar with, but that's why we're going over them right now. So a scalar has magnitude, meaning it has a specific size or amount of something. So it describes how much of that thing you have. All right, it does, again, it just tells us how much, right? It gives us an amount of a certain item, right? It tells us the amount of time we have, or how big an object is, how big its mass is. It can tell us the distance, right? How far an object has traveled. These are all examples of scalar quantities. Now we could also have vectors, and vectors you might not be as familiar with. This is a term that we use in physics a lot, but they tell us a little bit more than scalars. Vectors tell us the magnitude and direction of that thing we are trying to describe, okay? So in contrast to scalars telling us how much, vectors tell us how much and where that object is, okay? So it could, an example of a vector is velocity or force or displacement. If you are thinking about drawing vectors and scalars on a line, right? If you're talking about a coordinate diagram, an XY coordinate diagram, a scalar would simply be a line. We know this line is 2 meters long in this scalar example right here. And I will highlight that. Okay, so we know that's 2 meters. The contrast between a scalar and a vector is the vector gives us a direction. So this vector line here is telling us it's 2 meters long, but it is also moving to the right. So that is an important thing to distinguish between vectors and scalars, right? The vector gives us the direction as well. So think about it this way. Vectors always have arrows to tell us where it's going. Scalars do not have arrows here. Okay, so let's talk about how we use vectors and scalars when we talk about distance and displacement. So the last thing we will be going over today is what is the difference between distance and displacement. So we've got another T-chart contrasting these two terms. So let's first go over distance. You should be pretty familiar with the term distance. You should have heard that before. So distance is simply the total path traveled by an object. We use the variable lowercase d to represent the distance traveled by an object, and distance is going to be measured in meters. So meters are our standard unit of measurement for measuring distance in physics class. In contrast, we have displacement. So displacement and distance are very similar, but displacement describes the distance between the starting point and the ending point of an object, right? So if you were thinking about the distance traveled, right? If we started at xi, which represents the initial position of an object, so you can see this down here in the bottom left corner, and we followed this pink path all the way, say we're hiking in the woods, follow this pink path all the way up to our final position of xf, which stands for the final position. So this pink line is the total distance traveled, right? That's what your, whatever you use to measure your steps would measure, your total distance traveled. However, if we were looking at it from a bird's eye view and we were just measuring the displacement, right, where we started to where we ended, we would use this green line to measure the displacement. So the displacement is always the shortest path traveled from, or not even traveled, right? It's the shortest path and the shortest distance between your starting point and your ending point. We do not care about how far you actually traveled. We simply want to know how far you have been displaced from your original starting point. That is what we use to define displacement. Okay, so again, displacement is simply the change in an object's position. And keep in mind that the main difference between a distance and displacement, distance is a scalar quantity and displacement is a vector quantity. So again, distance is simply telling us how far we've walked that day. Displacement is telling us how far we've walked in a certain direction. So again, the main difference is we have a scalar quantity with distance and a vector quantity when we're talking about displacement. And did not mean to draw that. Okay. The other thing to note about displacement, it is simply measuring the change in an object's position. So remember, we use the variable x to represent an object's position. We are going to add this little delta here. This triangle is what we call a delta to represent our variable for displacement. So this delta, this triangle here, is basically the Greek letter for change. And remember that x means position. So we use delta x as our variable for displacement, because displacement describes the change in an object's position. Now, displacement is also measured in meters, just like distance. But again, displacement only cares about how your position has changed. It does not care about your total path traveled. It just cares about the change in your position from your starting position. Our equation that we use for distance and displacement, or excuse me, just displacement, is delta x is equal to x final minus x initial. So I represent x final with that little f, which is what we call a subscript after the x, and a little I after the other x to represent the initial position. So we call those subscripts. They're simply there to represent, because we do have two different positions here, your final position and your initial position. So we use a little f to represent your final position and a little I to represent the initial position. So let's do an example problem, because I feel like this is going to be a lot more clear once we work out an example in these notes here. So I'm going to zoom in right here. So here's our example. Lisa walks to her friend's house along the path to the left. What was her distance? What was her displacement? So the first thing that we need to do is, when we're solving physics word problems, is obviously draw a picture. Thankfully, we already have a picture drawn for us. So now we need to determine what we know and what we don't know. For the sake of time, I'm not going to draw a T-chart, but if you need to draw a T-chart, I always recommend drawing a little T-chart and separating what you know and what you don't know from the problem. I'm simply going to annotate this image of her path to represent what we know and what we don't know. So she is starting in her position right here. So I'm going to just go ahead and label that. Wherever our starting position is, we know that that is going to be xi. So that's our initial position here. Okay. And we know that she finishes right here at this finish position. So I'm going to go ahead and label that as, let's just change my colors a little bit, as XF. That represents our final position. So we've got XI and XF. Okay, then we also know she walks along this path to get to her friend's house. So she goes north 20 meters, then she goes east 30 meters, then she goes north another 10 meters, then she goes east another 15 meters, and then she finally goes south, whatever this distance is. So it looks like we will have to solve for this distance right now. Okay, so got our path, we got our starting and ending position. Let's first solve for our distance. So we know every piece of that distance except for this last part here where she is traveling south. So I'm going to go ahead and solve for what that is once she's traveling south. So I'm going to look at my two values where I'm traveling north, because this looks like these are on an even plane, right? The starting position is even with the finished position. So all I really need to do is add these two values of where she traveled north to figure out how many meters she had to walk back south to get to this same plane as her starting position. So I'm going to add 20 plus 10. And that is going to be equal to 30 meters. So we know that she walked 30 meters south again to get to her finish point. So to calculate the distance, all we're going to do is add up this whole distance, each part of this path that she traveled to get our distance. So I'm going to make a little space here for calculating distance. Okay, remember our variable for calculating distance is d. So now I'm just going to add up each little part that she walked to get our total distance traveled. So she starts off 20 meters walking north. Then she walks 30 meters east. Then she walks another 10 meters north. Then she walks 15 meters east again. And finally, we just calculated that she walks another 30 meters south to get her to her finish point, for her final position. So I'm going to add all of these together now to get her total distance. So 20 plus 30, I'm just typing this into my calculator, plus 10 plus 15 plus 30 equals a total distance of 105 meters. And remember, distance is a scalar quantity, so that is all we need there. We do not need to include the direction that she walked. That is her total path traveled. Now, in contrast, let's make a little space for talking about her displacement and calculating her displacement. Now remember, her displacement, we are only concerned about the shortest path between her initial position, again, her initial position right here, and her final position. So we are only concerned about this path right here for her displacement. So we are talking about this path, right? We are just concerned, since these are on the same plane going up and down, right? Starting position and the finishing position are pretty even with each other. So we are only concerned about how far east. I'm going to undo that. We are only concerned about how far east she walked. We do not need to worry about north and south because it is pretty even right there. So if I'm calculating how far east she walks, I want to know and calculate, add these two numbers together, right? So if let's let our initial position equal 0, and we are going to add the amount of walking she did east to get our final position. So our final position is going to equal 30 meters from right here, plus 15 meters. 30 plus 15 is going to equal 45 meters east. Sorry. Okay, so she walked 45 meters in that direction. So I'm going to add 45 right here. Okay, so our displacement, again, the way we would calculate this, if we're looking at our equation is that delta x equals xf minus xi. So our final position minus our initial position. So I'm going to plug in our equation right here. Xf minus xi. Okay, so we're starting off with xi. We already said that that was equal to, I'm just going to do this in a different color. We already know that xi was equal to 0. We're just going to let xi equal 0. She has not started walking yet at xi. So I'm going to say 0 right here. Our final position we already calculated is 45 meters. She walked 45 meters east. So I'm going to plug in 45 right here. Again, this is we're calculating displacement here. Now 45 minus 0 is simply 45 meters. But remember, displacement is a vector quantity, so we need to add a direction. So I'm going to say that the displacement, our final answer for displacement is 45 meters east. So notice the difference between our displacement, 45 meters east, and our distance. Total distance travel is 105 meters. So despite Lisa walking 105 meters to get to her friend's house, her total displacement is only 45 meters east from her starting point. So hopefully this is starting to come together, and just go ahead and write your 1 to 2 sentence summary about what you learned from watching this video. And I look forward to discussing this in class more with you soon.